So, in the fabrication process inevitably we have an effective overlap length between the gate and the source and drain regions. If this is the metal gate Vg and we have the drain and the source. So, there is an effective overlap between the gate terminal and the source and drain region, and in fact, it happens to be important to maintain this overlap because it facilitates continuous channel. Because of process variation, suppose in certain cases the channel ends here, the gate ends here, then you will not have the gate or the channel region completely in contact with the source and drain. So, by mistake, suppose in process variation the channel ends right here, the gate ends right here, then the channel will be broken. So, it is safer to have this overlap. So, intentionally also process technology allow this effective overlap length, and that is the technology parameter. TSMC 180 nanometer will have a characteristics overlap length which is present in their device. So, that depends upon the foundry's process. So, this region, the positive charge on the gate which is uniformly distributed all throughout the metal. If I zoom out this region and look at the phenomena that is happening there. So, in this region whatever positive charge you are putting, that is not balanced by the channel charge, right. We said that the positive charge in this region are balanced by the negative charge in the channel, right. Whatever positive charge you put in the middle region just above the channel, that is balanced by the negative charge in the channel, but positive charge on the metal which is overlapped with the source and drain region, that is balanced by a large number of electrons already present in the N plus region. So, more electron get attracted and accumulated towards this oxide interface, and that is how these get balanced. So, it is not dependent upon whether the channel is created or not created, it is always present, whether it is saturation, whether it is triode, off condition, this charge is always going to be present, because the moment you put some positive charge here, you are attracting more number of negative charges towards the oxide interface, and that leads to an effective capacitive effect, capacitive phenomena, and that can be also incorporated or clubbed with the CGS or CGD. So, both CGS as well as CGD are going to have this effective component, which is once again dependent upon the L overlap, the W and the COX. So, C overlap can be just written as COX times L times W, that is epsilon OX upon TOX times L times W, because that is L overlap, sorry. So, L overlap is the overlap length multiplied by W gives you the area of this effective capacitance coming between gate and source and gate and drain, they are always present. So, I can write down for saturation region CGS effective is going to be 2 by 3 COX WL plus the C overlap. Likewise, CGD effective only C overlap, because there is no capacitance coming because of the channel charge, only have the overlap capacitance. Now, let us also talk about the junction capacitance. So, we know that in a diode, when you are having some reverse bias applied, you are having say N type and P type, you are having some positive charges in the depletion region on N side and some negative charges on depletion region on the P side, and there is electric field. And if you are applying say a reverse bias, a DC reverse bias, say VR, and then you are on the top of this you are applying some AC signal trying to change the VR, either making a little bit more positive, a little bit more negative. So, result of this is expansion and compression of this depletion region, right. So, if you make the VR more positive, we know that the depletion region of the diode increases, it widens, right. If this is the W depletion, that is the depletion region of the diode, it is proportional to VBI, the built in potential, plus VR. So, if you are increasing the reverse bias potential, the depletion region increases, as a result the stored charges increase. So, once again whenever you are trying to apply a AC signal across this diode, there is a charge storage mechanism which is increasing or decreasing the stored charge in this device, and that once again leads to a charge storage mechanism. So, I can define this junction capacitance as dq junction by dV junction. What is the change in the charge across the junction that you obtain by changing the voltage a little bit? That is going to be the definition of junction capacitance. So, in general, this can be a nonlinear relationship. As we see, the W depletion is dependent upon the root under VR, and likewise the total channel charge is going to depend upon root under VR. So, dq by dV is going to depend upon 1 upon root under VR. So, we can say this is going to be something like root under VR relationship. So, the same phenomena of junction capacitance, that is the charge storage mechanism, is present in the MOSFET, because MOSFET inherently has this PN junction inbuilt between the N plus source and drain and the substrate for the NMOS, and likewise P plus source and drain and the substrate for the PMOS. So, once again, whenever we are changing the overall potential between the source, say let us call it drain, and the substrate. So, substrate potential, we have seen that it needs another contact. So, you can assume there is a P plus contact for the substrate. So, this is the body terminal as we have seen. I am not drawing the source part, let me draw that also. N plus is the source. So, here whenever we are increasing the drain potential, we are making this diode between the P and the N more reverse bias. So, we are going to increase the effective depletion region formed between the N plus drain and the substrate, and therefore, we are again playing with the stored charge in the depletion region, and that leads to the effective junction capacitance. And we can clearly see that this again is going to depend upon the total area, that is the W of the MOSFET. So, here we have to look into the direction perpendicular to the paper, to the sheet, and that determines the total W of the MOSFET, and then you have the dimension for the junction, you can call it xj. So, the total effective capacitance is going to depend upon this cross section area of the junction, that is contact with the P plus region, that determines the effective junction area, and that is proportional to the W. So, what you can say is the junction capacitance is going to be proportional to W. If you have a larger W, the junction capacitance will increase. Now, this is regarding the definition. Okay, this is how we define the capacitance, the junction capacitance, the overlap capacitance, and the capacitance arising from the channel charge between VG D and VG S. So, what is the significance of these capacitances in real circuit operation? So, this can be understood from the point of view of, say, small signal analysis. So, for example, if I take this diode, and as I said, I am injecting a current. So, for example, suppose I am having a DC current source across this diode. So, I am putting some DC bias, call it I diode, and we know that there is an exponential relationship. So, I diode is equal to I saturation exp Vd upon Vt, which is Kt by Q. So, this is the exponential relationship approximately for the diode. So, that is going to develop some Vd across the diode, right. So, there is some Vd across the diode, suppose it is reverse bias. So, Vd is higher on the N side. Now, if I want to say step up the current from Id to delta Id, Id plus delta Id, I am applying a small change in current. So, suppose my DC current is something like this, I have Id to begin with, I am stepping it up Id plus small id, and then again stepping it down in the opposite direction, making it id minus delta id, and I keep on doing this. So, as compared to the DC id, I have I am increasing and decreasing the current injected into the diode. So, if I do not consider the capacitive effect, I do not consider the charge storage effect across this device, what is the behavior of V diode, that is the effective potential drop across the diode that we expect. If I do not consider this charge storage mechanism, we expect that the moment you ramp up this current to I d plus delta I d, the voltage across the diode will also go up according to this expression, right, because I d is increasing, V d should also increase. So, ideal condition without considering the capacitance, the V d should also go up and down as compared to the DC level. In reference to the DC level, it should just keep going down. So, this was the DC V d across the diode. On the top of that, we are imposing some small V d, increase and decrease in the opposite direction, commensurate with the increase and decrease in the current. That is the ideal case without considering charge storage. But now, if we consider the charge storage mechanism, we know that in order to change the V d, we will need to expand or reduce this charge stored, and that charge stored, it is whenever you are trying to change this charge, increase or decrease this charge, that will happen only after a finite duration, after integration of this current, right. So, the additional charge that you are trying to get, that is going to come because of the integration of the current. So, that is going to take some I dt charge. So, if you are talking about delta I d, that will integrate over a time and then only give you the additional charge delta q, small I d dt, and that is going to result in an effective potential drop V d, small signal drop across V d. So, it is not going to be instantaneous. So, as a result, what we expect is there is going to be some finite delay, the actual waveform is going to have some finite delay in rising up and again falling down. It is not going to ideally just go up and down. So, we see that whenever there is a charge storage mechanism present, the signal change over here, it is becoming sluggish, it is getting delayed, because you need to integrate that change in current to accommodate or produce that additional charge which is present in the depletion region. Same thing we can say for the junction capacitances in the MOSFET. Likewise, another example that we can take is the gate of the MOSFET. Suppose you are having a ideal current source I d, which you are supplying to a resistance R g, which is connected between the gate of the MOSFET and ground. You have a R d connected between the say V d d and the drain of the MOSFET, and the source is once again say grounded. On the top of this, if I impose another pulse current source just like this one, and as a result I change the total current going in. So, the total current going in, it will be I, which is equal to I d, which is the DC current source. This is constant, but on the top of that I am applying this small signal I d going up down up down. So, I have plus I d. So, ideally, if I do not consider the capacitance of the MOSFET, if I do not consider the charge storage mechanism inside this MOSFET, so the moment I d goes up, the voltage also goes up, right. So, in total current I, if I plot, as compared to this I am putting it up and down by small I d. Ideal, if I ignore charge storage mechanism, the total gate voltage V g instantaneously will go up and down. This voltage level is just I d times R g, right. So, the DC level is I g times R g, and on the top of that, if I am changing this current by small I d, it will go up and down instantaneously. And this level, this difference, we can call it small V g, which is equal to I d times R g. This will have this much jump every time you increase the I d by small I d, the gate voltage should increase instantaneously, reduce instantaneously, if I do not consider the capacitive behavior or the charge storage mechanism of the MOSFET. But ideally, once again, what is going to happen, in order to increase the voltage over here, you are effectively changing the VGS, and whenever you change the VGS, this positive charges must be balanced by equal amount of additional negative charges in the channel. So, whenever you are trying to increase this gate voltage, it must be compensated by equal increase of negative charges inside the channel. So, that the electric field is once again neutralized. So, the electrostatics will force the electrons over here to accumulate and balance the additional positive charge that you are trying to produce. For the negative cycle of the ID, you are trying to reduce the positive charge here, that is you are trying to reduce the voltage over here, that means it is going to reduce the negative charge over here. So, once again this charge storage will not change instantaneously, you need to provide, you need to integrate the current over here for a finite duration, whatever is the small current going to the MOSFET, I call it IG. So, whatever is the current going here to the gate of the MOSFET, it will integrate ID dt, and that is going to provide over a time t naught, it is going to provide delta q, that is the total additional charge that you are putting on the gate of the MOSFET, delta qg, and corresponding to that the change in the gate to source voltage can be written as delta qg by cgs. So, delta vg will be just delta qg upon cgs by definition, that because cgs is defined as qgs times vg, right, or in other words cgs is equal to del vg upon del qg. Now, that means that once again, rather than this voltage going instantaneously up and down, it will take finite amount of time to rise and fall. So, this is the real characteristics, right. So, once again because of this charge storage mechanism, we are not able to change this voltage instantaneously, likewise we are not able to change the channel charge instantaneously, it will respond after a delay when you have been able to integrate the required amount of additional charge to produce the new VGS across the MOSFET, that is between the gate and the source. So, this is how we can understand the effect of parasitic capacitances. So, it is not that we have additional capacitances connected between the gate and source or gate and drain, it is originating because of the basic physics based operation of the MOSFET. The physics of the MOSFET is inherently producing this charge storage mechanism, and in order to change the gate voltage, you need to change the total charge stored across this oxide both on the gate as well as in the channel, and for doing that you need to integrate this current for a finite amount of time to produce that delta q and hence to produce the delta v, and therefore, you are having an equivalent RC effect. So, it is something like replacing this MOSFET by a equivalent capacitance over here. So, I can model this MOSFET by an equivalent capacitance, where the capacitance is defined as small signal CGS approximately for the time being, ignoring the CGD, and it is accounting for the charge storage mechanism. So, what we see from here, without even going into circuit analysis, doing small signal frequency response and all those, we can conclude that whenever we have this kind of charge storage mechanism present in the device, it is going to slow down my operation. Rather than an ideal high speed, it is going to slow down my signal transition and affect the speed at which the circuit can perform. If the CGS is larger and larger, this curve will be more and more sluggish, and therefore, the speed at which the circuit is operating will be more and more sluggish, right. So, that is the basic effect that these parasitic capacitances produce. They are slowing down your circuit, they are slowing down the circuit response, and as a result of which your overall circuit performance, speed, bandwidth is going to suffer. Therefore, we call them parasitic capacitances. Their role or their importance becomes more significant at higher frequencies, because at lower frequency the time duration is much larger, the curve, the period of the signal is much larger, then as compared to the period, the signal will be able to rise much quickly. So, we can ignore this finite rise and fall time. So, at lower frequency their effect is not that much visible, but as we go towards higher and higher frequency, the signal may not be even able to follow, the gate charge may not be even able to follow the input current. As a result, this may become more and more sluggish and the amplitude may reduce. So, the effect of these small parasitic capacitances arising from the charge storage mechanism becomes more and more prominent at higher frequency, and therefore, the parasitic capacitances, their role comes into picture for high frequency response and not so much for low frequency. For low frequency operation, we can treat them almost absent. We say that they are all acting like open circuits. That can also be understood from the point of view of complex impedances on the capacitance. So, if you are having the complex impedance of the capacitance ZC defined as 1 upon omega C, if you will include the phase factor iota omega C, for larger frequencies their impedance reduces, and therefore, they can no longer be treated as short circuits. We need to take into account their finite impedances. At low frequencies 1 upon omega C becomes very large, and therefore, we can almost ignore them because their capacitance values are pretty small. It may be for 180 nanometer technology, I would say if I look at 1 micrometer channel length, the CGS will be of the order of few femtofarad. CGD will be relatively smaller, as we see CGD is just coming because of the overlap. So, CGD will be approximately a fraction of femtofarad, 0.2, 0.3 femtofarad. So, their effect becomes more and more prominent at higher frequency, and therefore, we include these parasitics for high frequency model of the MOSFET. Let me add these capacitances that we just defined on the MOSFET model. So, we define CGS, I will just call it CGS, earlier term used was C effective, but let us call it CGS. This is equal to 2 by 3 COX WL plus C overlap in saturation region. We define CGD, which is just equal to C overlap for saturation region. We define the junction capacitance, which is coming between drain and the body. I can call it CDB. It is the junction capacitance Cj, and it is a function of course of Vd and Vb, because it is the diode across which we are measuring this capacitance, which is appearing between drain and body. And likewise, we have CSB, which is again the junction capacitance dependent upon the Vs and the Vb. So, in general, for normal MOSFET operations, NMOS substrate will be always preferably kept at ground potential or 0 potential, because we do not want to forward bias the diodes. If you increase the body potential, the PN junction associated with the P substrate and N source, P substrate and the drain junction can get forward bias. So, it is preferred that the substrate of the NMOS is kept at lowest potential, that is at 0 voltage, if 0 is the lowest potential available to you in the IC. Source can be at a higher potential than 0. In many circuits, we may see that the source is going to be slightly higher potential than 0. Drain is definitely higher than the source. So, drain to body junction is always reverse bias. Source to body junction can be either at equilibrium, provided the in case the source is at 0, the source as well as body both are at 0. If source is at higher potential, then this is also reverse bias. So, both these junction capacitances are coming because of the reverse biased diode associated with the drain and junction, source and junction, and likewise we have the other capacitances between the gate and source, gate and drain, coming because of the channel charge modulation and the C overlap, and CGD comes only because of the C overlap. So, this basically completes our high frequency model. So, if I replace this MOSFET model with the corresponding small signal model that we have just seen. So, we will start with the small signal model GM VGS RO, and then we had this terminal drain and the gate and the source. This is the earlier model, the low frequency model that we started with. Now, we need to connect these capacitances. I can define another terminal, call it the body terminal over here, and I can draw the capacitances between these two terminals. So, between the gate and the source, between the gate and the drain, I have CGD, between the gate and the source I have CGS, between the source and the body I have CSB, and between the drain and the body I may have CDB. So, this is the high frequency model including the small signal parasitic capacitances arising from the core device physics of the MOSFET, and we are going to see how to analyze circuits in for high frequency regions where we need to take into account these parasitic capacitances. So, before I proceed, let me stop here and see if there is any question. Let me see. So, we have some questions collected. Yeah. So, CGD, as I said, yeah, means one of the question is whether CGD is equal to C overlap. So, yeah, means as we said in saturation region we do not have the control of drain voltage on the channel charge. So, if I go back to my original earlier slide, if the device is in saturation, the channel charge is pinched off. On the drain side you do not have much channel charge. If you increase the drain voltage little bit, there will be some pushing of this channel towards the source, but the total change in channel charge will be very insignificant. Therefore, approximately we assume that the effect of VD on channel charge is almost negligible. Therefore, del Q channel by del VDS or VDG is going to be almost negligible, that component is negligible, but we do have the overlap capacitance which is always present, that does not need the channel to be present, right. So, that is what we discussed. So, you have a channel you have a the overlap region, the charges on the gate are being balanced by negative charges in the N plus region. So, that does not require channel to be present, channel can be completely depleted, even if it is off you do have the effective C overlap present between the gate and the drain under all conditions, likewise for the source. So, for saturation region, because we do not have the CGD because of the channel charge, the only capacitance between CGD that arises in the depletion in the saturation region is the C overlap. Okay. So, yeah. So, another question probably again requiring some more discussion on the topic of circuit response or speed response, effect of parasitic capacitances on the speed response. So, once again revisiting this particular example, what we said is, if you do not consider the charge storage mechanism, if you do not consider the capacitive behavior of the MOSFET, I assume that there is no current flowing into the gate, right. Ideally, MOSFET does not have any current flowing into the gate. It is, if you talk about DC current, there is no current flowing into the gate of the MOSFET. DC current is 0. Therefore, there should not be any current here. Whenever I increase the ID to ID plus delta ID, that entire increase in the current should immediately go to RG, and therefore, the gate voltage should immediately go up from ID RG to ID plus small ID times RG. So, we are expecting an instantaneous jump in the gate voltage, because it is just controlled by RG, we are not considering the capacitive behavior of the MOSFET. But we know that in order to arrive at this larger Vg, which is higher by ID RG, because this voltage we are expecting that when we increase the current to ID plus small ID, the gate voltage will increase by ID times RG. But in order to increase that much gate voltage, I must also ensure equal amount of negative charges being produced in the channel, so that this additional positive charge, which is ID RG times this effective capacitance, that is balanced by the negative charge. So, in order to allow this effective additional positive charge, I must divert some of the current to the MOS gate. Initially, some part of the current will be utilized in increasing the positive charge count on the gate. So, this MOSFET gate is stealing away some charge, that current is not passing through the oxide, there is no current, but the gate is accumulating that positive charge for some duration till the effective VGS across this MOSFET is equal to the final value, because this is the final value we expect, right. For long duration, if I apply this additional ID, the final value should settle to ID RG plus small ID RG, but that additional voltage will mandate more positive charge on the gate and more negative charge in the channel. And that means that initially when you are increasing the ID to ID plus delta ID, some amount of the current or some amount of the positive charge will be stolen by this gate to increase the positive charge count and hence increase the voltage. It will not happen instantaneously. So, the current in ID RD will not jump instantaneously from ID to ID plus delta ID. First it will be diverted to the gate of the MOSFET, store some more positive charge, and then finally once it has reached to the steady state value, again the rest of the entire small ID will start flowing from RG. Then the output, the gate voltage settles to the final value. So, that is because of the charge storage mechanism. So, once again I can replace this MOSFET by equivalent small signal capacitance CGS and say that when you are having this CGS and then you are trying to increase ID to ID plus delta ID, there is going to be RC time constant associated with the charging of this capacitor. The voltage across this capacitor will not jump instantaneously, because for that you need infinite amount of current. So, you will take some finite amount of time to increase the voltage across this capacitor by integrating the small current flowing into the capacitor for finite duration, then only the voltage of the capacitor will gradually rise and reach the final value. If the CGS is larger and larger, if this effective capacitance between this point and ground is larger and larger, you are going to take more and more time to integrate the current and cause the same voltage increase. So, your waveform is going to be more sluggish, and as a result your circuit response is going to be slower, because you are trying to increase the gate voltage instantaneously by increasing the drain gate current, but this capacitance, because of the charge storage mechanism, is slowing down your behavior. Same thing will happen on the drain side as well. So, here because you are trying to increase the drain voltage instantaneously by increasing the gate voltage, but we know that there is again a effective charge storage mechanism between the drain and the gate, drain and the bulk. So, whenever you are trying to increase the drain voltage, the effective potential across the drain and the gate, drain and the bulk, also it will take certain time to settle to the final value, because you have a charge storage mechanism associated with this. So, you have some effective capacitance between the drain and the gate, and also between drain and the bulk. Assuming that the bulk is grounded, you cannot change the voltage on this capacitor instantaneously. It will take some finite amount of time for this additional gate voltage to produce the required additional current in the drain, and then change the voltage across this capacitor. So, it will have some RC time delay associated with the charging and discharging of this parasitic capacitor, and that produces sluggish response, slows down the response of your circuit. That is the basic mechanism. We can always do the mathematical analysis, we can always find out the complex impedance of the capacitance and do the network analysis by KCL, KVL, find out the frequency domain transfer function, but the basic mechanism how the circuit is slowed down is because of the charge storage mechanism of this parasitic capacitances. That is the origin. Another question: if CGD is 0, charge concentration, what happens to the charge concentration? Conservation. So, CGD is it's not. So, if CGD is 0, in that case you are just saying that the overlap length is 0. So, effectively if I assume that the overlap length is 0, we are not going to have any CGD, and therefore, in this small signal model, if I look at the capacitance coming between the drain and the gate, that will be absent. So, that does not violate my charge conservation in any manner. Only thing is you do not have a charge storage associated with the change in drain to gate voltage. No, the junction capacitance is not. There is another question is whether there is any link between the CGD and the junction capacitance. So, ideally there is no link between the junction capacitance is arising because of a completely different phenomena. So, the CGD is appearing because of the depletion region between the drain and the source, whereas the CGD is appearing because of the overlap capacitance in saturation region. So, CDB has no such direct link with CGD. And another question regarding the dependency on junction capacitance on W. So, yeah, we have already shown that ultimately the junction capacitance depends upon the area. So, if I look at this junction, it is going to extend towards the W. So, this entire area of this junction, this bottom plate and this side wall is going to give you the junction capacitance, because the depletion region is surrounding this entire junction. So, it is proportional to W and the junction depth. So, larger is the W, larger is the junction capacitance. Okay. So, now we have completed the high frequency model of the MOSFET. The Next thing that we need to look into is the noise model, the noise analysis associated with MOSFET. So, any more question before we proceed towards noise model? Now, let me talk about the noise model, although we have a little time left before we leave for the break. So, I would prefer if there is any other question before I go for the noise model. Any other broad question? Yeah. So, GMB, there is another question, a good question on GMB that we have not discussed, which can also be important. So, we have skipped this in favor of time because we already are running short of time, and the GMB will require discussion of threshold voltage. How does the threshold voltage depends upon the substrate to source potential, and what is the dependency? From there we can apply, we can figure out the expression for GM. So, given the time constraint, it will be difficult to cover that, because that requires consideration of threshold voltage, the origin of threshold voltage, physics behind it, then we can derive the small signal parameter. But first thing is talking about the threshold voltage, and I am afraid we may not have enough time to go into that detail. We can give you references. Of course, in certain cases GMB can be important, and there are some interesting circuit schemes where GMB can be used for some interesting signal processing applications. So, that is true, but we are skipping that. Hot electron, another question is on hot electron. So, those are short channel effects. Those are more important, I would say, for digital circuits, where the channel lengths are very short and you can have very large electric field within the short channel that can create hot electron effects. For analog circuits, the starting point was that mostly we may be going for relatively larger channel lengths, because we want larger RO, larger output impedance, stronger saturation region characteristics. Therefore, hot electron effect may not play very important role unless your DC voltage at the drain is very high. There are certain reliability issues, definitely. If your DC voltage at the drain is sufficiently high, you can have hot electron effect, you can have some reliability issues, you can have NBTI, PBTI, which are related to somehow the electric field, high electric field created in the drain region or in the channel vicinity to the drain region. But once again, they are the hot electron effect is more of a reliability issue associated with the short channel devices. We may not focus too much on that and while considering the analog circuit design. Any other question? I guess we can start with the noise model in the next slot rather than starting it right now. Okay. So, just a brief introduction about noise. So, we have so far studied about the parasitic capacitances, the high frequency model, the low frequency small signal model. We have looked into the physics of the devices, how these capacitances are coming, and how do we understand the effect of these capacitances on the device behavior and ultimately the circuit behavior. So, now let us talk about the noise model. How do we include the effect of noise? How does noise originate? What is the physical mechanisms behind this? So, once again, we may not be able to go into the detail of the device physics and its derivation, but at the higher level, accepting certain formulations, accepting certain well known facts, we are just going to formulate the noise model, which can be incorporated into the small signal model that we have developed so far, and then see how they are going to be used. Before we go towards the noise model of the MOSFET, it is first of all important to understand how noise is represented in circuits. So, what is the concept of mean square noise or RMS noise? What is the how are you going to add different noise sources? If you have two different independent noise sources available, how do you add them? Can we directly superimpose them, or we need to do something else? What do we do to their power, noise power or mean square value? Likewise, we also need to see what is meant by noise spectral density. So, one thing is the amplitude of noise, or the magnitude of the voltage or current fluctuation because of noise that may be produced in a device. The other important characteristics is what is the frequency spectrum of noise, how is it distributed in frequency. So, if you have any signal, I can take a frequency response and find out what is the frequency spectrum, at which frequency it is peaking. That means at that frequency the signal content is highest, or in other words, the signal is having that particular frequency content maximally. So, likewise, we also need to look into the frequency characteristic, the spectrum of the noise sources. So, in general, there are two main categories of noise sources which are encountered in device in terms of spectrum. One of them is white noise, where the frequency spectrum is white, it is flat. That means all frequencies starting from 0 to infinite, they have almost equal magnitude of noise component. Other dominant frequency spectrum that is encountered in devices, which creates a lot of problems, especially for low power, low noise circuit design, is 1 upon f noise, whose spectrum is, it increases with 1 upon f. At lower frequencies, the noise becomes steeper and steeper, higher and higher, and therefore, when we are dealing with low signals, we are trying to amplify or process low frequency signals coming from sensors, biomedical sensors, or any different kinds of sensors. That low frequency noise becomes very critical and it corrupts the signal, and therefore, we need to take certain special considerations to handle that low frequency noise at circuit level. So, we will be looking into these two noise sources, the noise source with 1 upon f characteristics and noise source with white characteristics, and we will look into the origin of these two noise sources in the device very briefly, trying to formulate the expressions, compact expression, trying to make sense of that expression, not going into the derivation, just trying to justify that expression, and then use that noise model in incorporate that noise model in our small signal analysis. So, there are three things we are going to do. First is definition of noise, representation of noise in time domain, addition of independent noise sources. Second thing is frequency domain representation of noise in form of noise spectral density, and the third thing is incorporating noise model in the MOSFET, understanding the origin of noise in the MOSFET and including small signal parameters corresponding to the noise model in our model to complete the entire picture, low frequency, high frequency, and then the noise. So, this recipe will help us in doing the analysis for the circuits that we are going to encounter, doing the DC analysis based on the DC equation, doing the small signal analysis based on the small signal low frequency equations, looking at frequency response, bandwidth of the circuits resulting from the parasitic capacitances, and finally talking about the noise analysis because of the key noise sources in the transistors and also the resistors. Resistors are another component which inherently have voltage or current, equivalent current noise present in them, and that is related to the transport of electrons. So, when you are having electrons being transported across a resistive channel, it propagates in a zigzag fashion. You have a lot of carriers colliding with the crystal, with the lattice, and it is not a straight line, it is not like a bullet, it follows a zigzag pattern, lot of collisions, lot of scattering takes place, and because of these scattering and collisions, there is an effective thermal fluctuation, effective thermal voltage created across the two terminals of that device. So, without going into details, we can understand that this origin of the noise voltage in a resistor, it is basically because of this random temperature dependent fluctuation of the electron trajectory or carrier trajectory in that device. And we can expect that if your resistance is larger, that means your collisions encountered by the carriers is stronger, or they are having longer channel or path to traverse, resulting in longer resistance. We expect that this noise voltage is going to be larger, because that effective random fluctuation is going to be larger. Likewise, if the temperature of the device goes up, then once again this random thermal motion is going to increase, and as a result of which the effective noise voltage across the two terminals of the resistor is going to increase. There are two things that are coming into picture: the effective equivalent resistance value, larger is the resistance value, more is the random nature or random fluctuation in the trajectory of this carrier, leading to effective larger noise voltage, and then higher is the temperature, larger is the thermal fluctuation in the trajectory, once again larger is the noise voltage. So, we can say the effective noise voltage produced across a resistor of value R is proportional to two things. One is the R and second is the T, and the proportionality constant happens to be 4 K. The K is the Boltzmann constant. So, the effective noise voltage across the resistor is 4 KTR. That is the starting point, and that is the without we have not gone into the frequency domain representation of the noise, but we will do that soon when we start again. So, this is the noise spectral density of the noise voltage produced by a resistor of value R. So, let us continue from here. Let us look into these 3 points when we come back, that is the representation of noise, manipulation, addition, subtraction of noise, representation of noise in MOSFET and its capturing it in the frequency the small signal model that we have discussed so far. Thanks a lot.